what we're going to talk about today is how we're going to analyze circuits that are excited at multiple frequencies. So I'm going to call this multi-frequency circuit analysis. So I'm going to draw a relatively simple circuit here. So let's say that I have the following circuit where I've got some sinusoidal voltage source. I'm going to call this guy right here Vs of t. Um, let's say that this is a 16 ohm resistor. This will be a 1/5 of a farad capacitance. This will be a 2 Henry inductance. Here I will have a 20 ohm resistor. And then on this side of things, I will have a sinusoidal current source. Let's call this Is of t, like so. And our ultimate goal here would be for us to find this voltage drop, which I'm just going to call Vx of t. And where things will get interesting, so to speak, is going to be here where I define my sources. So let's say that my sinusoidal voltage source is 15 cosine of 2t plus 10 degrees volts. And Is of t is going to be 250 sine 3t plus 70 degrees milliamps. So we have two different sources here, and they are oscillating at different frequencies, okay? So we have an example here of a circuit that is excited at multiple frequencies. Now, we haven't talked about this in circuits one. We're just now introducing it in circuits two, but this is actually a fairly common scenario, okay? Um, every single one of our radios, communication systems and things like that is a multi-frequency system. Sometimes we'll deal with multi-frequency circuits where one of those frequencies is effectively DC, and then we have AC signals superimposed on top of it and all of that kind of stuff. Same process applies here. So how do you guys think that we are going to handle a circuit like this? Any thoughts? Yeah, so effectively what we're going to wind up doing is superposition, where we're going to analyze the circuit at each frequency and then add those results together at the end. Because if our circuit is a linear system, meaning that it's composed entirely of resistors, capacitors, inductors that don't vary in time, we should be able to use just conventional circuit analysis techniques at each individual frequency. So that's going to allow us to still use our frequency domain or phasor circuit analysis techniques, as opposed to getting into the nightmare of analyzing this circuit in the time domain, but now we have multiple frequencies to deal with, okay? So very good assumption there, because you're absolutely right, okay? So if we're trying to find Vx of t, let me just put solution here, all right? we would need to analyze this circuit twice because we have two different excitation frequencies to deal with, okay? So let's start with our analysis at what I'm going to call omega 1 is equal to 2 radians per second, okay? So this is our case where our voltage source is on and our current source is off. So the circuit that we are analyzing is going to look like this. So I'm going to draw it in the frequency domain. So I'm going to use the phasor representation of my voltage. So that would look like 15 angle 10 degrees. Volts. My 16 ohm resistor stays a 16 ohm resistor. Let's see, I'm going to have one, actually, let's do this way. 1 over 1/5 times 2 comes out to be a minus J 2.5 ohm impedance for that. Sorry, that should be a capacitance. I don't know why I drew it. So minus J 2.5 ohms here. This is going to look like a J4 ohm impedance over here. Bless you. Here's a 20 ohm resistor, and then my current source, because it's excited at a different frequency, is going to be turned off. And so that's why I'm replacing it with that open circuit. And then this is our voltage Vx prime that we are interested in. So now that we are here, we'd simply just use whatever circuit analysis method makes the most sense to us. For me personally, I would probably wind up doing either voltage division, or I would do a source transformation and then Ohm's law here. So voltage division seems fairly straightforward. Source transformation and Ohm's law also fairly straightforward. You could do nodal mesh, any of those other things if you really wanted to, but not particularly necessary for this guy. So which way do you guys want to look at this? Voltage division. Okay. So using voltage division, I could say that my voltage Vx prime is going to be my known voltage. So that's 15 angle 0 degrees volts. Then I'm going to have the ratio of my impedances. So the impedance that I'm finding the voltage drop over is that minus J 2.5 ohms in parallel with J4 ohms. So that's going to look like minus J 2.5 ohms times J 4 ohms divided by minus J 2.5 ohms plus J 4 ohms, all divided by 16 ohms plus what I have in my numerator, minus J 2.5 times J4 over minus J 2.5 plus J4. And I'll now throw this into my calculator real quick. Why would the voltage source? Oh, 10 degrees. Thank you. Yes. I thought you meant 10 volts in magnitude, and I was rather confused, but you are correct. I erroneously put a phase angle of 0 degrees instead of 10 degrees. So thank you for that catch. Good job. Oh, son of a bitch. Sorry, I accidentally pressed the table button on my calculator and that literally erased everything that I had typed in. So now I have to start this over. Goodness gracious. Sorry about that. All right. So I believe I've got everything typed in correctly. And I got a voltage of 5.769 with an angle of negative 57.380 degrees volts. If anybody else suffered through typing all of that crap into their calculator, could you please? So you get the same number, Carl, or you're raising your hand as a question? Question.
The 2 rad per second? Where did that come from?
So when we look at our voltage source right here, that is our omega 1. And then when we do our analysis at our second frequency, this 3 right here is going to be the omega 2 that we use. So omega is always the number that is being multiplied by time inside of our sinusoidal signal. So that is our angular frequency of excitation. And for what it's worth, omega divided by 2 pi is the linear frequency of excitation, which here in the US, for industrial settings and stuff like that, we use 60 hertz. So that's the 60 hertz is F for transmission and distribution here in the States. 50 hertz is what's used in most of Europe. And we'll talk about that a little bit more when we deal with, power and all that kind of stuff over the next few class meetings. So this is the voltage that I got for Vx prime using voltage division. I'm going to assume I typed everything into my calculator correctly, and we'll move on to the next thing. Okay. So now we need to analyze our circuit at our second angular frequency. Okay. So this will be omega 2 is equal to 3 radians per second. And since yes, Nikolai.
10.7 angle negative 170 degrees.
I, for what it's worth, don't see an error in what I typed in. Which I mean, obviously you probably don't see an error in what you typed in either. I'm more concerned about the process here than the number being exactly right. So I'm going to assume that that's correct, but if it's not correct, the process is correct. And that's what I'm really worried about here. Okay. Because I don't want to spend another 5 damn minutes. Yeah. So now we're going to analyze our circuit at our second frequency of interest. So in this case, this is essentially the case where our current source is on and our voltage source is off. So I'm replacing my voltage source with a short circuit because it's an off voltage source. Here is my 16 ohm resistor. And because we're at a different excitation frequency, the impedance of our capacitor and the impedance of our inductor are now going to be different, okay? So this is why we have to use superposition, because these impedances are frequency dependent, and since we've got 2 different frequencies, we can't have our capacitor and inductor look like 2 different impedances at the same time. So bless you. This guy over here is obviously just going to be a simple J6 ohms. I need to use the calculator for what's going on with the capacitor. So that's 1/5 times 3. So that's going to look like negative J 5/3 of an ohm here. And this is going to be my current source. So note that my current source was defined as a sine function. So that means that I'm going to have to convert that sine function to a cosine function. So that's going to look like 250 cosine 3t minus 20 milliamperes. Then I'm going to convert that into a phasor. So I'm going to choose to write this as 0.25 with an angle of negative 20 degrees amps, where 250 milliamps is obviously the same thing as 0.25 amps. And then that phase angle of negative 20 degrees is because I was given a sine function and I need to convert it to cosine. I do that by subtracting 90 degrees from my phase angle. And then lastly, this is the voltage that I am interested in, which I'm going to call Vx double prime. All right. So how would you guys care to go about determining this particular voltage? So current division, to find the current through any of either the J6 ohm impedance, the minus J 5/3 ohm impedance, or the 16 ohm impedance, and then we could use Ohm's law. But I would argue that we could actually do it in one step just by using Ohm's law from the jump. So what I mean by that specifically is that this current right here is that same 0.25 angle negative 20 degrees amps, right? So essentially, all of our current flows through the 20 ohm resistor before it hits those three impedances connected in parallel. So why couldn't we just use that current times those three impedances in parallel to get the voltage in one step? Okay, so that's what I'm going to do because current division is just going to make it take one more step, and I'm rather lazy or efficient, whatever way you feel like interpreting that. So I believe that we'll have Vx double prime will be equal to 0.25 angle negative 20 degrees amps. So that's our current divided, what the happening? Okay. So there's my current, and then I'm going to multiply it by 1 over, and then the sum of the reciprocals of those impedances. So I'm just going to put it over the sum of those reciprocals, and that's the same thing as multiplying by 1 over. So down here, I'll have 1 over 16 ohms, plus 1 over J6 ohms. And then I'm going to do minus 3 over J5 ohms. So that minus 3 over J5 is just that minus J 5/3 turned upside down. Everybody okay with that? Sorry, my stylus started behaving wonkily. So I'm going to throw this into my calculator, 0.25 with an angle of negative 20. divided by 1/16 plus 1/6i minus 3/5i is equal to 0.571 with an angle of negative 101.793 degrees volts. For what it's worth, I'm just going to point this out to you all. What we just did there is effectively Ohm's law using admittances, because all three of those things are connected in parallel. So just as a heads up.
One quick question.
Sure.
For the 3/5J,
Mm-hmm.
since you're subtracting that, why didn't you just keep it at just J 5/3, since that was already negative? So in this case, why would it not be positive since we flipped it back up?
So if I think I see what you're saying. So if I wanted to make this positive, I need to move the J to the numerator. So I could, I guess, technically do that. So what he's suggesting is effectively saying that I have -3/J5. If I multiply this by J/J, that's going to wind up giving me +3 times J/5. I could have put that there as well if I wanted to, but mathematically, there's no difference.
Yeah, but one big thing is when you flipped it, and then you subtracted it, when you're flipping it, where it's like 5J, -5J/3.
Mm-hmm.
When you're flipping it, doesn't that essentially make it, positive 3/5J?
So I think I understand what your question is. There's always a possibility that I made a mistake, but I don't believe that I did. So I have 1 over.
Oh, no, I see it now.
Okay.
That makes a lot more sense.
Yep. Okay. I concur. Once again, process-wise, I believe I've done this correctly. So what do I do now to find the voltage that I'm interested in? So Nikolai suggests that I combine them. He is, and I know this is going to sound silly, either right or wrong, depending on what he means by combine them. So this is one of the places where it actually gets kind of confusing. Every other time we've done superposition, we've simply added the results together. And we are going to do that, but we need to be very careful and make sure that we add the results together in the time domain and not the frequency domain. Because these two phasors, we could add them together and we will get a number, but that number is completely meaningless because each of these phasors is representative of a different frequency, right? We literally can't add them together in the frequency domain and get anything useful out of that. So we need to convert back into the time domain and then add those functions together. And that's actually going to be the voltage drop across these elements of interest here, okay? So that is a very, very common mistake, which is why I asked the question the way that I asked, okay? So what we're going to find is that Vx is going to be Vx prime as a function of time plus Vx double prime as a function of time. So that would look like 5.769 with an angle of -57. Oh, good God, nope. cosine, sorry, my brain stopped working for a moment there. Cosine of 2t minus 57.380 degrees plus 0.51 cosine of 3t minus 101.793 degrees volts. So my question to you guys is now, could we make that look like a single sinusoid? No, absolutely not. So two different frequencies is going to look like two different sinusoids added together. So for what it's worth, I'm going to throw this into Desmos just to kind of see what it looks like. Okay. So I'm going to call this first signal y1 as a function of x. And that's going to be equal to, I think it was 5.679 cosine 2x minus, sorry, my memory ran out. So 769 and then 57.380. That phase angle is in degrees, but this is by default in radians. So I'm going to multiply this by pi over 180 so that my total angle is now simply in radians. My second signal was 0. Let's see, 571 cosine 3t minus 101.793, thank you, multiplied by pi over 180. Oh, and I need to change that t to x because I don't remember how to set up multiple variables. And this guy down here is just going to be y1 plus y2. And I'm going to turn those other guys off. And we can see that this is very much not a single sinusoid because our amplitude appears to constantly be changing as we look at things from cycle to cycle, all that kind of good stuff. So for the most part, we have figured out how to analyze circuits at multiple frequencies. Obviously, if we had 3 or 4 different frequencies, then we'd have to analyze the circuit 3 or 4 different times. The reason, or one of the reasons why this is an incredibly important topic is actually going to come to you much later on in your electrical engineering career. Specifically when you start looking at what are called linear systems and signals in your junior year. You're going to learn a technique that's called the Fourier transform, okay? And the Fourier transform is effectively going to allow you to decompose practically any non-sinusoidal signal into the sum of a bunch of different sinusoidal signals added together. So we can make square waves, triangular waves, all of that kind of good stuff, really anything that we're interested in, we can decompose it into a whole bunch of sinusoids that are added together using this particular mathematical technique. And that allows us to use effectively steady state sinusoidal circuit analysis to analyze any input signal as long as we can decompose that input signal into sinusoids, okay? Typically speaking, we'll use computers to do that for us because it gets rather annoying rather quickly, but that is essentially what's going on is multi-frequency circuit analysis, analyzing the circuit at every frequency, adding the results together back in the time domain and getting the response that we're interested in. So that's the Fourier transform and inverse Fourier transform method of circuit analysis is literally what we just did on a much larger scale. So incredibly important part of communication systems engineering, and we're introducing it here. So this is where I would like to stop for today.